Hello, Doctor. We are Group A7. So here's our group members. And now I'm going to introduce part 1. So who plays it, Marshall? So for this part, basically, we just have to research all the rooms without any missing. For this part, we use 3 algorithms. So first one is DFS. So DFS algorithm is a graph traversal algorithm that explores as far as possible along each brand before backtracking. So it efficiently visiting all the rooms in the building in a path-like manner. And second one, we use Dijkstra algorithm. So for the Dijkstra algorithm, it is a path-finding algorithm that visits rooms in order of increasing distance from the start, ensuring that the shortest path to each room is found. And third one, we use BFS algorithm. So this algorithm is also a graph traversal algorithm that visits all the rooms level by level, ensuring that all the rooms on the same floor are visited before moving to the next floor. And next, I'm going to introduce DFS. So here's the pseudocode for the DFS algorithm. So in this algorithm, we prefer DFS traversal of the graphing starting from given start node. So this algorithm maintains a set of visit nodes to keep track of nodes that have been explored. So it's also used a stack to determine the order of the node's exploration. And then we pop a node from the stack, check if it has been visited before, and if not, we will mark it as visited. Then we do each neighbor of the current node and push any unvisited neighbors onto the stack. So this process continues until the stack is empty, ensuring that all the reachable nodes from the start node has been visited. And finally, the algorithm returns the set of the visit nodes and representing the order in which nodes were visited during the DFS. And now I'm gonna do the running time complexity. So in this case, V is the number of vertices, which stands for the number of rooms, and the E is the edges of the represent connection of the rooms. It's edges. And here's our program code for the DFS algorithm. So basically on this program code, we have the output like this, yeah. And next one is Dijkstra algorithm, and this is the pseudocode for the Dijkstra algorithm, and this is running time complexity. And we have the program code for this algorithm, and the output also like this. And next, we have the DFS algorithm. So we have the pseudocode for the DFS algorithm and the running time complexity, and then the program code. And basic on the BFS program code, we have the output also like this. So then we compare 3 algorithms together. Then we decide the DFS algorithm is the best solution because it has the fast time complexity at OV plus E compared to the OV times V of the Dijkstra algorithm. And DFS algorithm use less memory than the BFS because it's not necessary to store all the children of the node. And then we did a little bit improvements that we are considered. So for the limitation part, the Dijkstra algorithm quadratic time complexity is slow when the number of the vertical is large. And for the possible modification part, so if a binary heap is used, the time complexity as shown. And if a Fibonacci heap is used, the TC equals the equation as shown. And then I'm gonna run the part 1, the DFS algorithm really quick. And the output's gonna be like this. And that's all from the part 1. And I will pass to Yun Sun for the part 2.
So now let's look at part 2, cracking the chess code. So for this problem, we have to find a combination that will unlock the chess lock. So in this algorithm, we propose 3 solutions. The first one is a grid search, or more commonly known as a linear search algorithm. So it involves checking all the possible combinations systematically until the correct one is found. In this case, it will try 1,000 possible combination. The second one is random search. How it works is it involves trying random combination until the correct one is found. And the third one that we propose is called particle swarm optimization. It is a bio-inspired stochastic search algorithm with additional features that allows it to search faster if additional criteria for the search can be given. So now let's look at the first approach, the grid search, which is the best solution that we will reveal in a short while. So the pseudocode is this. It's very simple. It's a for loop that increments that search the sequence, the range in incremental order sequentially in the ascending order, right? So it is a for loop. It will try the combination. So the runtime complexity as this, the best case is constant times, and the average and worst case is O of n. N is the number of combination to try. So then let's look at the program code. We have the pin, and then we loop through until we find the pin. Here's the snapshot of the output, as you can see here. Now let's look at the random search. So one improvement that we have considered is that because the repeating sampling might cause the algorithm to sample the same combination over time. So what we can do is we can save the sample data to a list to prevent resampling. So this is the pseudocode. It will add the combination to a triad, and then over time the search space becomes smaller. With this, the runtime complexity is as follows. Here's the program code. As you can see, the list is getting smaller over time. And then here's the snapshot of the output. Third, let's look at particle swarm algorithm. Here's the pseudocode. Here's the runtime complexity. Here's the program code. Continue, and then the snapshot of the output. So the best approach that we decided is the grid search algorithm because it is the easiest to implement. It has the fast time complexity with a constant space compared to n compared to linear space for random. And then thirdly, PSO is a plausible solution. However, it is overkill for this kind of problem. The improvements that we have considered overall is that when you do grid search, Python for loop might be slow for ultra long sequences. One modification that you can make is vectorize the operation by using NumPy, or better known as SIMD. So now let's look at the run the source code. So this is the part 2. When we run, it will work seamlessly. So now let me pass it to my team member, Suzal, for part 3.
Okay, thank you, Yusung. And now I'm going to introduce about part 3. So part 3, basically, we have to find the different words from the 2 letters. For this part, we also use 3 algorithm. So first one, we use Livingston distance algorithm. So for this algorithm, it calculates the minimum number of the single character edits. So it requires to transform one letter into another. And it can be used to identify the different words between 2 letters. And next, we use Myers difference algorithm. So this algorithm efficiently finds the difference between 2 sequences. So in this case, are 2 letters by performing a line-by-line comparison and making it like suitable for the identifying the different words between 2 letters. And third one, we use Burford's algorithm. So this algorithm comparing like each word in one letter to every word into the other letter, iterating through all possible combinations to determine the different words between the 2 letters. So now I'm gonna go through with the Livingston distance, and we have the pseudocode for this algorithm and the running time complexity and the program code. And the screenshot of the output gonna be like this. And now I'm gonna do the Myers difference algorithm. So for this algorithm, we have the pseudocode like this, and I will explain like more specific in the program code part. And for the running time complexity part, in this case, so like the N is stands for like paragraph 1, and M is like paragraph 2. So the D is like the number of the different words. So in this case, if there's only one difference in the like paragraph, the time complexity will be like really fast. But if there's like 10 more difference in this paragraph, the time complexity will like be very slow. And then we are gonna move into the program code part. So for this Myers difference algorithm part, so that we spell the paragraph into like individual words using the spell methods. So and then we're gonna like match it. We initialize the matrix with the like learn words 1 plus 1 and the learn words 2 plus 1. So where the words 1 and words 2 are the words arrays of the 2 paragraphs. And the step 3 is like the matrix is step 2, the matrix is like filled by iterating over the words like in the both paragraphs. And if the words like at the current position are equal, so the corresponding the matrix entry is set to the value of the top left edges entry plus 1. So otherwise, if it's set to the maximum value between the entry above and the entry to the set 1, so it will like starting from the bottom right corner of the matrix. Yeah. And a traceback is performed to find the difference between the 2 paragraphs. So if the words at the like current position are equal, so the indices are like decrement, and if the left adjacent entry is greater than the top entry, the word is like appended to the different words 2 list, and the G index is like decrement. So other words, the word is appended to the like different words 1 list, and the I index is like decrement 1. So after the traceback, so any remaining words in the first paragraph are added to the different words 2, and any other like remaining words in the like second paragraph are added to the like different words 1. So the resulting lists are reserved into store the like the original words order, and then the different words in each paragraph are gonna be printed. And here's like the screenshot of this output. And then we have the brute force algorithm, and we have the pseudocode for this algorithm, the running time complexity, and also the program code. The screenshot of the program code is going to be like this. So after we compare 3 algorithms, we decide the solution to Myers difference algorithm is the best solution because it has the most efficient in the real world scenario where the D is small. And then for the Livingston algorithm, the distance will consider all the possible edit operator at each step, which can make it be very slow. And then for the brute force is like in particular for large input due to like quadratic words average case time complexity. And now we are going to move to the improvements that we are considered. So for the limitation part, the Livingston distance algorithm time complexity and space-time time complexity is O(n) plus O times n, and where m and n are the length of the 2 strings, so it can be like the quiet resource and for the longer strings and for the possible modification. So we can use like this algorithm and to optimize the version of the Livingston distance that reduce like space complexity to the linear. And now I'm gonna run the Myers algorithm for the part 3 really quick. So run it, and the output is a different like this. And that's all for me. Thank you.
So let's continue with part 4. Part 4, we basically have to find a bulk in a sorted list of bulk in the library. So here we can use linear search, jump search, and binary search. Linear search is basically searching the bulk sequentially. Jump search is searching sequentially as well, but jump ahead by fixed step. over the list of elements. And then binary search is you divide the list into half, and then the item is compared with the middle element. If it matched, then it is returned, or else the list is divided again if based on whether it should be on the left or right, since the whole list is sorted. So now let's look at the first approach, which is the linear search. Here's the pseudocode runtime complexity, program code, snapshot of the input output. Second, we have the jump search, pseudocode runtime complexity. This has a square root runtime complexity, interesting. And then program code, snapshot of input output. Thirdly, we have binary search, right? So binary search, like I said, here's the pseudocode. What we do is that first we initialize the low, the high, and then we have a clause that checks when the low is when the high when the logic is no longer true. That means that you have searched through the entire list of the library, right? Then it will return the book is not found. Or else, if the book is at the middle position, then it will return the book found at the middle position. If the book is more than the middle, means the book is on the right side of the list, then it will search the right side recursively. If the book is on the left side, then that means it is less than the middle. So, okay, that's the basic logic. The runtime complexity is the fastest. It is O of log n. N is the number of books in the library. And then now let's look at the program code here. So you have the binary search function here, and then I run the binary search. I will show you the complete code in a short while. Here's a snapshot. You find the book, the 7th book in the shelf. The best approach, like I said, is the binary search algorithm, because it has the best time complexity among the 3 potential algorithms. It doesn't require you to make any assumption of the distribution of the book, such as interpolation search. And so now let's look at improvements. If m searches are needed to be performed, this will cause the time complexity to be O of n times n. The possible modification is to use a hash table or dictionary in Python to save the book list, thus achieving constant time lookups. Now let's look at the code here. So the code here, part 4, I have linear search, jump search, binary search. Now, if you look at the book list, here's the book list, right? If you count 1, 2, 3, 4, 5, 6, 7, the book that we are searching is on the 7th place. I need to run this to initialize the library, and I run. You can see that 7 book on the list. So that's all from us. Thank you very much.
Right. So the part 5, this secret message was created by using Caesar cipher encoder. A Caesar cipher is a simple method of encoding messages. It employs a substitution method wherein letters in the alphabets are shifted by a fixed number of positions to produce an encoded alphabet. The algorithm used brute force, frequency analysis, and known plain text. A brute force attack is a technique used to decode a Caesar cipher by systematically trying all the possible keys or shifts until the correct one is found. And frequency analysis is a technique used to decode a cipher by analyzing the frequency distribution of letters in the ciphertext and assume that distribution of letters in the ciphertext reflects the distribution of letters in the original language. The third one, known plain text attack, is a technique used to decode a cipher when the attacker has access to both the plain text and its corresponding ciphertext. The first approach is brute force attack, but this is not the chosen one. So briefly, this is the pseudocode, this is the running time complexity, this is the program code, which later I will run, and this is a snapshot of the output. And second approach is the frequency analysis. This is the chosen one. So let's go through the pseudocode. There are 3 functions which are decrypt message. This function receives ciphertext and shift value as input. First, we declare output to store the decrypted message. Then we look through each char in the ciphertext. If the char is non-alphabetic letter, it will be appended right away to the output. If the char is an alphabet, we will get the index, which is the ASCII value of the char in lowercase. Then, char correspond to the new ASCII table will be assigned to the new char, which later will be appended to the plain text. After that, we will check if the old char is in uppercase, then the new char will be in uppercase as well, and vice versa. For average difference function, it will receive text from decrypt message. This function will count the frequency of every letters in the text using the library counter. The next line actually calculate the difference between frequency of letter in the text and the expected frequency. Then they will add the difference of every letter, then return the average of difference. For shift function, it will receive the ciphertext as input. In for loop with key value equivalent to 1 until 26, it will call decrypt message function and average difference function. For every key, it will choose the key with the lowest difference between, because the lower the difference, the more likely the plain text to be the answer. It will return the key which has the lowest difference. The running time complexity, the worst time complexity is ON if the ciphertext is long. The best case will be of 1 if the ciphertext is empty or has a length of 1. The average case time complexity is difficult to determine precisely as it depends on the distribution of letters in the ciphertext, but it can be approximated as ON. This is the program code, and this is the snapshot of the output. The third approach is a non-plain text. This is not the algorithm we choose. So briefly, there are two functions, build key function and decode function, and we must know the non-plain text and its corresponding ciphertext. Running time complexity. This is the program code. This is the snapshot. The best approach to this problem is frequency analysis, because firstly, frequency analysis is more effective when applied to longer ciphertext. It relies on analyzing the frequency distribution of letter in the ciphertext to deduce the key. Secondly, it does not require non-plain text as clue. Non-plain text are text which require both the ciphertext and its corresponding plain text are not suitable in this scenario since no plain text were provided beforehand. Thirdly, frequency analysis make educated value in shifting by calculating the average difference, unlike brute force attack, which do not leverage any specific knowledge about the cipher or the plain text. They simply try all the possible combinations, which means they are not efficient in terms of time or computational resources. This code of frequency analysis algorithm can be used only if the plain text is in English, because the dictionary of letter frequency contains the approximate frequency of letter in the English language only. Thus, for possible modification, we can implement language detection algorithms such as a language model and machine learning classifier beforehand to determine the language. So let's run the code. This is for brute force attack. As you can see, it will try all the possible keys and the answer in shift 5. This is the chosen one, which is frequency analysis algorithm. This is the dictionary, the letter frequency dictionary in English language. So this is the answer. And this one is the non-plain text algorithm. As you can see, the answer is key 5. This means that in key 5, the average difference is the lowest among all the other keys.
Hi, I'm Sophia. I'm going to proceed with part 6. Okay, so for this part, we've been given a table with few items and their corresponding weight. We've also been given the maximum weight that the trolley can carry, which is 30 kilograms. And we are asked to find which of these items was carried on the trolley. Okay, so to solve this problem, I've come up with 3 possible approaches, which are knapsack, brute force, and backtracking algorithm. So knapsack algorithm utilizes dynamic programming to solve optimization problems by considering the value and weight of each item and determine the optimal selection within a capacity constraint. While brute force algorithm is an approach that exhaustively explores all possible combinations to a problem by generating and evaluating all combinations. And lastly, backtracking algorithm is an algorithm that is incrementally builds a solution candidate and explores the solution space by backtracking whenever an invalid candidate is encountered. Now I'll explain more about the first approach, which is knapsack algorithm. So this is the pseudocode for this algorithm. Firstly, we prompt the user to enter the number of items. Then we create a list to store the maximum values. Then the dynamic programming loop started. Okay, so in this loop, we iterate from 1 to total number of items, which is n, and then it will iterate from the maximum weight capacity to the current weight. And then we will calculate the maximum value at the current capacity by comparing the maximum value at the current capacity with the value of the current item plus the maximum value obtained by excluding the item. Then we need to determine the items included in the knapsack. If the current item was included, we will check if the maximum values at the current capacity is the same or not with the maximum value obtained by excluding the current item. If it is not the same, means the current item is included and will be added into the selected item list. Lastly, it will return the maximum value at the given capacity and the list of selected items. Next, the running time complexity. So this is the running time complexity, where n is the number of items and w is the maximum weight capacity of the trolley. And then here is the program code, as I explained in the pseudocode before. And then this is the snapshot of the output. So moving on to the second approach, which is brute force algorithm. So the next, so this is the pseudocode, which we're not going deep into this one because we did not choose this algorithm. So this is the running time complexity, where it is an exponential time complexity, which is O2 to the power of n. So since we're trying all possible combination of items to find the solution, and we have 4 items, so the number of possible combination is 2 to the power of 4. Therefore, the time complexity is O2 to the power of n, where n is the number of items. And here is the code and the snapshot of the output. And then the third approach, which is backtracking algorithm. So this is the pseudocode. And again, because of the time constraint, we did not choose this algorithm, so we won't going deep into this one. So this is the running time complexity, the same one as the brute force algorithm, and then the program code and the snapshot of output. And then moving on to the next part of the presentation, which is limitation and modification. So firstly, memory usage, which could be solved by implementing algorithm using a space optimized approach. For example, we use 0-1 upset algorithm. So this kind of modification reduces the memory usage by only storing the necessary information for the current and previous row of the table instead of the entire table. Next, the exponential time complexity. We can modify this limitation by memorization or caching. So we can store and reuse previously computed result to avoid redundant computation and reduces the time complexity by eliminating unnecessary exploration of the same subproblems. And to conclude, for this part, we decided to choose the first approach, which is knapsack algorithm. So this is because the time complexity, which is efficient compared to the other two algorithms, which is brute force and backtracking. And then its efficiency because it implemented dynamic programming approach, which can handle reasonably large problem sizes efficiently. And last but not least, the scalability, since it can handle larger problem instances more effectively compared to the other two algorithms, which could be computationally expensive due to their exponential time complexity. So we're going to move on with the code for part 6. Okay, so since we decided to choose the knapsack algorithm, so I'm going to explain about this one. Okay, so this is the dynamic programming where we use in the knapsack algorithm. So actually, we will use this dynamic programming to fill in the table with maximum weight that can be carried for each combination of items. So this is the output for this part, which is we will get the 4 pieces of tires of the car in the garage and a set of corn for the kitchen at the barn.
Hello, my name is Siti Mariam Azlina and I will be presenting for the part 7. So part 7 is that the given question is to solve the secret message of jumbled words to real message. From the given 4 words of unarranged, we have to find the real message behind it so that the detective could find another clue in order for him to catch the culprit. So the jumbled word problem involves decoding a set of words that have been scrambled or rearranged. So the objective is to match each jumbled word with its corresponding correct word from a given set of real words. The goal is to find the best match based on certain criteria such as similarity, scores, or pattern matching. So I have given 3 approaches for this solution. Is that the first one is the brute force. Secondly is frequency-based, and last but not least, anagram-based. So for the first approach, which is brute force, we generate all possible permutations of the jumbled word and check each permutation against the word set to find valid words. This approach can be time-consuming and impractical for large word sets. So this is the pseudocode for this approach. The running time complexity, which is the best case, is O1. Average case and worst case is linearly, which is ON. So the left side is the program code and the right side is the output of this code. Secondly, which is the frequency-based. Frequency-based is basically we create frequency distributions of letters in both the jumbled word and the words in the word set. We compare the distributions to identify potential matches. This approach works well when the jumbled word and the word set have similar letter frequency. This is the pseudocode for this approach, and this is the running time complexity, which is the best case is j times n, the average case is j times k times n, and the worst case is j times k times n to the O of 2. The left side is the program code and the right side is the output for this code. Last but not least, the third approach, which is anagram-based. Anagram-based is basically we generate anagrams of the jumbled word and compare them with the words in the word set. So an anagram is a word formed by rearranging the letters of another word. So this approach can be effective for finding valid words with the same set of letters. This is a pseudocode for this approach, which is the calculate similarity score function takes two words, word 1 and word 2, and calculates the similarity score based on the frequency of letters in each word. It uses a frequency counter to count the occurrences of each letter in the words and then compares the ranks of the letters' frequencies. The score is calculated as the sum of the absolute differences between the ranks, and the match jumble words function takes a list of jumble words and a list of real words. It iterates over each jumble word and finds the best match among the real words by calculating the similarity score using the calculate similarity score function. The best match is the one with the lowest score. So the function will return a list of tuples where each tuple contains a jumble word and its best match real word. So the running time complexity for this approach is that the base case is linear, which is OG, and the average case is J times K, and the worst case is J times K times N. To the left side is the program code for this approach, and the right side is the output for this code. So the improvements that can be considered, which is the limitation of this code, is that it assumes the jumble words are formed by rearranging the letters of the original words without any additional or substitute letters. And the possible modification that we can do is that we consider techniques like edit distance, which measures the number of insertions, deletions, or substitutions required to transform the jumble word into a real word, which is allowing for more flexible transformations. The best approach for this problem is the third approach, which is the anagram based. So the reason are, the first one is that this is suitable for small word lists and jumble words consisting of rearranged letters. Secondly, it is straightforward implementation that compares sorted characters of words. And last but not least, it is because it is language independent and applicable to various languages. Next, I will show the run code for this approach, for this part. So the first one, which is the brute force approach. So the output is that that person has motive here. And then the second solution, frequency based, same, the output. And last but not least, the anagram based. This is the output for this solution.
Hi, now I'm going to present part 8, which is about who is the most probably murderer. We have 3 solutions for this problem. First is the well-based suspect selection. We select the suspect based on their net worth. The smaller net worth is the higher motive. Next is the relationship analysis algorithm. Focus on the relationship and character of each family member. Third is the character-based motive analysis. Only focus on characters of each family member. Here is the pseudocode of well-based suspect selection. The time complexity of this algorithm is O n log n. Here's the program code. Its output shows that Will Masha, his uncle, is the most probably murderer. Now is the relationship analysis algorithm. We have one function that finds the most probably murderer to sort the score in ascending order. Another function is to calculate the motive score based on relationship and character. The closer relationships will be assigned a higher motive score, and the worst character has a highest motive score. Then declare the family members and finally print the result. Time complexity is O n log n. Here is the program code. Here is the pseudocodes of character-based motive analysis. The time complexity for this algorithm is O n m. Here is the program code. Its output shows that George Masha, his son, is the most probably murderer. The limitations and modifications for these algorithms are limited scope, focus on characters only. Expanding the scope can contribute to determine the motive behind a crime. Incomplete characters information can impact the analysis results and lead to incorrect assumptions about motive. Take steps to ensure the consistency and accuracy of the character's description used in the algorithm. In case where limited or unreliable information is available, the algorithm effectiveness may be compromised. Treat the algorithms as a dynamic system that can evolve and improve over time. We choose the relationship analysis algorithms to be the best approach to this problem. It is because it considers more than one factors and emphasizes the analysis of interpersonal dynamic and conflict within the family. Best case ON, where N is the numbers of family members. This occurs when the first family members have the highest motive score. Average case. The sort operations have an average case time complexity of O(n) log n using efficient sorting algorithm. In the worst case, O(n) log n, the algorithms need to iterate through each family members to calculate the motive score and perform a sort operations on the score list. Now I'm going to show the code. For relationship analysis algorithm, and here is the code. And when we run it, we can see that it is the output for this algorithm. Here we come to the last part, which is the final chapter. There are two murderers who killed Mr. Masha. The murderers are his son, Jonas Masha, and his uncle, Will Masha. First, we know that Mr. Masha stated the murder have a strong motive. We know that his son is always true to his father. This happened after Mr. Masha doesn't want him to be the heirs of his huge business. His uncle cooperated with his son to poison him on this day. The clue that we got actually is pointing to the murderer. The book's title, Great Winter's Night Fun Times, indicate Jonas Masha. I remember when I was young, Mr. Masha spent time with Jonas and me on a winter night. It was a memorable time for us. However, his son became rude to him after knowing he would not be the heirs of his business at the age of 18. After that, they are not as close as before anymore. Mr. Masha did tell me before that he is disappointed that his son would treat him this way because of his business. His son is good at managing businesses, but not good at managing good relationship with people. Mr. Masha always hoped that his heirs will be able to serve people in their business with a whole heart and well manner. Another hint is based on the message I found in one of the areas. Mr. Masha left the message by using the items he get. We observed deeply that 4 tires and corns for chickens are taken from the car garage and the bar. The areas that intercept this area is the garden show. Will Masha is a retired army officer. Mr. Masha offered him to be the gardener for his medicine. It is because his uncle doesn't want to work in any other places, so Mr. Masha let him manage the garden. You might be wondering why he wants to murder Mr. Masha who gave him a job. Actually, Jonas is the main planner for this murder. He always wanted to revenge on his father. He once again requests Mr. Masha to think again about his decision on giving his business to his sister. However, Mr. Masha decided, although Jonas proved his ability to manage the business by having his own business, Mr. Masha told him, we have to serve people with our hearts, not only focus on the profit. The words made Jonas more angry as his father, so he planned this murder. However, he doesn't want to do it on his own. He thinks he can push away the responsibility to another person if the murder is not successful. So he found Will Masha, who needed money to pay for his debt. Unfortunately, Will Masha cannot get any money now, and yet he decided to point out Jonas Masha as well. That's all from us. Thank you for listening. Hope you like our story.